So the question in front of us says, find the area bounded between the three curves, y equals x, y equals 1, and y equals x squared divided by 9, as shown in the following picture. We're looking at finding this area with integrating with respect to x. And so when we're integrating and we're trying to find the area between two curves, we want to look at what is our top function and what is our bottom function. And so I can see that our function is changing, which is on top and what is on bottom. And our function on top right here for this first piece is y equals x. And if I look below, this piece right in here is x squared divided by 9. And so let's look at setting up the integral for just that little piece, that lighter shaded blue in the picture. And so if we do that, we're looking at the integral. Our value of x where we're starting is at 0. And the value of x where we're ending in this picture is at 1. Our top function here is x, so we look at the top function x minus the bottom function, which in this case is x squared divided by 9 dx. So that just gives us the area of this first piece. And so now let's look at adding, and let's get the area of that second piece. And so my bounds for that second piece is 1 to 3. And our top bound, top function, is this horizontal line here, which is y equals 1. So I'm going to have the top equation, a function on top, 1 plus, sorry, not plus, minus this bottom piece, which is still x squared divided by 9 dx. Okay, so we're going to go through, we're going to take the antiderivative of each piece. So taking the antiderivative of x, we're adding 1 to the exponent. So that gives us an x squared and dividing by our new exponent of 2. Minus taking the antiderivative of x squared. I'm going to pull the 1/9 out here. So taking the antiderivative of x squared, we get x cubed over 3. And we're evaluating this from 0 to 1. Plus, so antiderivative of a constant is that constant times x. So that's just going to be 1x or x minus, and again, the antiderivative of 1/9 x squared is 1/9 x cubed over 3. And that piece is from 1 to 3. Okay, so recall that when we're looking at definite integrals, we're first plugging in the upper bound wherever we see an x. And then we're going in and we're plugging in the lower bound wherever we see an x. So plugging in 1 wherever we see an x, we have 1 squared, which is 1, divided by 2, minus 1/9 all times 1 cubed, which is 1, divided by 3, minus, so normally we would put parentheses around that whole function because we're subtracting off that whole function in here. But I notice when I plug in 0, wherever I see an x, I'm just going to get 0 left for that piece. So it's not too bad. So then we're going to add, looking at the other piece, now plugging in our top bound for that second integral. So we're plugging in 3 wherever we see an x in here. So I get 3 minus 1/9, 3 cubed, which is 27, divided by 3, minus, so this is where it is important to put the parentheses. So now going back in and plugging in 1 wherever we saw an x. So we got this 1 minus 1/9 times 1 cubed, which is 1, all divided by 3. So simplifying everything down, let's see what we have. We have 1/2 minus 1/27 And then we have, I noticed that let's see. Well, 9 times 3 is 27 over here, right? In this denominator. And then we have 27 in the top. So this technically right here, that's just 1. So I have 3 minus 1 in this piece. So 3 minus 1 gives us plus 2. And then distributing our negative sign, I get this is minus 1 and then plus 1 over 27. Okay, so combining like terms, I just noticed that I have some common denominators already and that those cancel out. I have a negative 1 over 27 plus a 1 over 27. I have 1/2 left. And then I have plus 2 minus 1, which is just plus 1. So 1/2 plus 1 gives us back 3/2. So we found that area below that curve or in between those two curves was 3/2. We don't know what the units are, but it would be units squared if we had the units. So let's look at the second part to this question. But before I do that, I'm just going to pause the video and see if there's any questions. Okay, so now looking at the second part to this question, it says find the area with integrating with respect to y. Well, I pulled my picture, but I need to pull my equations too. Well, let's just first look at this. And so if I'm integrating with respect to y, we're kind of changing our axes and we're looking at it as our bounds are going to be for our values of y. Our bottom bound here is 1 and our top bound, was 0 and the top bound is 1. If I look at it, the equation to the furthest to the right, we're going to use this equation, y equals x squared divided by 9 as the furthest equation away. The problem is that I need to write this in terms of x equals. And so to do this, let's solve this in terms for x. And so I could multiply both sides of my equation by 9. And so I would get 9y is equal to x squared. And then I could take the square root of both sides. So the square root plus or minus 9y equals x. I notice though that my x values are always positive in this picture. And so I'm just going to look at x equals, and I'm going to simplify this. Square root of 9 is 3. And then I have the square root of y. But I know I'm going to integrate. And so when I integrate, I'm going to have to rewrite the square root of y as y to the 1/2 power. So we have x equals 3, y to the 1/2 power. So I have my bounds. My lower bound for the y is 0. The upper bound for my y is 1. My curve that is furthest away is this 3y squared. And then minus. So now I have to look at the curve that's closest to the y-axis. Well, it's this right here. And so notice if I do it with respect to y, we only have to do one integration. And so this value here was y equals x. So it's already in terms of x equals y. And so this would be minus y. And then instead of dx, because it's integration with respect to y, we put dy. Okay, so now we're just going to add 1 to our exponent. So we have 3y cubed over 3 minus the antiderivative of y is y squared over 2. And we're evaluating this from 0 to 1. So if we go in and we do direct substitution, and those 3's cancel, we would get 1 cubed, which is 1, minus, what's wrong? Sorry, it's looking like something's wrong. Let me just pause the video for a second and find that. Okay, what I did was I didn't copy down what X was correctly. This is X is equal to 3y to the 1/2 power. So let me just erase this again. Okay, so we're going to add 1 to our exponent. So that's going to give us 3y. Adding 1 to 1/2 gives us 3/2. We're going to divide by 3/2, which is the same thing as multiplying by the reciprocal, which is 2/3. There we go. And then the antiderivative of a y, so minus, is y squared over 2. Now we're evaluating this from 0 to 1. Before I start plugging in, I notice that I can cancel my 3's. And so now we have 2, plugging in our top bound of 1. We get 1 raised to the 3/2 power minus 1 squared all over 2. And then minus, but if I go back in and plug in 0 or wherever I see a y, I just get back 0. So 1 to the 3/2 power is just 1. So 1 times the 2 out front is 2 minus 1/2. And so that's going to give me 3/2 squared units. And so if you didn't get the same area, because it doesn't matter which axis we're integrating with, if we didn't get the same answer, then you know that you did something wrong going through this. Okay, so looking at the definite integral in front of us, we have the integral of x minus 1 over x, and then that quantity is times the quantity x plus 1 over x. And so it's not in a form that we know how to integrate yet. And so sometimes we can just manipulate this integrand so that we can integrate it. And so I noticed that we can distribute. I also notice that I have x minus 1 over x and x plus 1 over x. So those are a difference of 2 squares. So if I distributed that out, that's the same thing as the first term squared minus the second term squared. So I have the integral of x squared minus 1 over x quantity squared. So I have the integral of x squared minus 1 over x squared dx. And so we can rewrite the one piece, the 1 over x squared, as x to the negative 2 power, bringing that piece up into the numerator. And so now we have the integrand is x squared minus x raised to the negative 2 power dx. And so these are now both pieces of the integrand are in the form that we know how to integrate. And so we're just adding 1 to our exponent, which would give me an x cubed divided by my new exponent of 3, minus adding 1 to negative 2 gives me back negative 1, dividing by negative 1, plus c. And so rewriting this a little bit, I have x cubed over 3, a minus and negative, so this is really plus, and I can bring down that x to the negative 1 down to the denominator, so I could rewrite that as 1 over x plus c. Okay, so looking at the following, we have the definite integral from 0 to 1/2 of x cubed, and this is all divided by the square root of 1 minus x to the 4th dx. So you're probably going to have a page of integrals. You might even have 2 pages of integrals, some definite, some indefinite. Looking at this, there's no way I can manipulate this with rewriting it. And so I'm looking to see if I can use substitution. I know I'm going to have a problem when I integrate anything with a radical and I have more than one term underneath. And so I'm going to choose my u to be this 1 minus x to the 4th. So I need to figure out what dx is. And I can do this by differentiating both sides of what I chose u to be. So differentiating u, I get 1 du equals the derivative of 1 is 0, and the derivative of negative x to the 4th is negative 4x cubed dx. So let's get dx by itself. And we can do that by dividing both sides by what's in front of the dx, which is the negative 4 over x cubed. So this is x equals. So if I go back and plug in what I chose u to be, I got x cubed over the square root of u dx, but dx we just found was this du over negative 4 x cubed. So normally if you choose things correctly, all the variable x's or whatever we're trying to differentiate originally, or taking the antiderivative of originally, is going to cancel out. And so it does, our x cubes cancel. And I can rewrite this a little bit. So I can kind of pull this negative 1/4 out here. And I could actually put it in front of the integral if I wanted. And the square root of u in the denominator, I'm just going to bring it up into the numerator and change the sign of the exponent as negative 1/2 du. My values here are x, and I could change my bounds now. I think changing the bounds now is easier than having to go back and do substitution in the end and keeping the bounds the same. So let's change our bounds now. So for x equals 0, we're going to plug in 0 into the equation what we chose u to be, and that's going to give us what u is then. And so I can see when I plug in 0 for x in here, I get that u is equal to 1. So down here, u is 1. And then now we're going to look at x equals 1/2. So when x is equal to 1/2, this would give me, I got to do a little more work, u is equal to 1 minus 1/2 to the 4th power. So u is equal to 1 minus 1 to the 4th is 1, 2 to the 4th is 16. I'm just going to get a common denominator. 1 is 16 over 16. So I have 16 minus 1/16 is 15 over 16. So in this case, u is equal to 15 over 16. So now we're in the form that we can go through and integrate. And we don't have to change our bounds back to x after we take the antiderivative, or not the bounds, the antiderivative. Okay, so taking the antiderivative of negative 1/4 u to the negative 1/2, we're adding 1 to our exponent. So negative 1/2 plus 1 is positive 1/2. And dividing by 1/2 is the same thing as multiplying by the reciprocal. So multiplying by 2 over 1. And then we're going to evaluate this from 1 to 15 over 16. Okay, so plugging in our bounds. Let's simplify first. 2 and 4 both have a 2 in common. So we are left with a negative 1/2 coefficient out front. And now plugging in our upper bound, wherever we see a u, we have u to the 1/2 is the square root. So we have the square root of 15 over 16 minus Now plugging in 1 wherever we see the u. So minus then the negative 1/2 square root of 1. So I have negative 1/2 square root of 15, and can break down the square root of a fraction as the square root of the numerator over the square root of the denominator, over the square root of 16, which I know is 4, minus a negative, so plus 1/2. And so I get negative square root of 15 all over 8 plus 1/2. I'm just going to write a single fraction, but you could just leave it like that if you'd like. So we have negative square root of 15 plus 4 all over our common denominator of 8. Okay, so the problem in front of us now says y is equal to the absolute value of negative 1 plus x plus 2, and y is equal to negative 1/5 x plus 7. The question said, graph the following functions and then find the area bounded between the two curves. So I noticed that we have an absolute value function. And so we can rewrite our absolute value function as the following. So remember, this is the same thing as two separate equations. It's the same thing as y equals negative 1 plus x. And this is if x is, let's see, if x is greater than or equal to 1. And then we get the equation if we plug in a negative in front. So it's the negative of what's inside the absolute value, negative 1 plus x. If x is less than 1.
So we would still be including the +2 afterwards.
Thank you. Yes, we will be including that +2 after. And so we can kind of then simplify this each one down then. And so this first piece, this would be y is equal to 2 minus 1. So this would be 1 plus x. If x is greater than or equal to 1. And this one right here is going to be y is equal to, so if I distribute my negative 1s, I'm going to get this is equal to negative x. And I'm going to have a positive 1 plus 2, so this is really plus 3. If x is less than 1. We need to know when are these two equations, when are those going to be intersecting one another? And so let's set those two equations equal to each other. So we're looking at when is this absolute value of negative 1 plus x, end of absolute value, and then plus 2. When is this equal to the other equation, which is negative 1/5 x plus 7? So recall when you're looking at solving equations with absolute values, the first step is to isolate that absolute value. So we're going to do that by moving that 2 over to the other side by subtracting 2 to both sides. And so we would get the absolute value. I'm going to just rewrite this as x minus 1 instead of minus 1 plus x. So absolute value of x minus 1 is equal to negative 1/5 x plus 5. So to drop this absolute value, I would have two separate equations. I would have what's inside the absolute value equal to the positive or whatever the other side was, which is, so x minus 1 is equal to negative 1/5 x plus 5, or what's inside the absolute value, x minus 1 is equal to the negative of everything on the other side. So negative of the quantity negative 1/5 x plus 5. So let's just work with the first equation and let's clear our fractions. You don't have to, but I just tend to not like to work with fractions. So I notice I can clear my fractions here if I multiply everything through by 5. And so on the left-hand side, distributing my 5, I get this 5x minus 5 is equal to distributing 5 on the right-hand side. Well, the 5 cancels with a negative 1/5, just leaving me with negative x plus 5 times 5, which is 25. So I notice that I'm left with a linear equation. And I'm just going to get x's to one side of my equation and anything without an x to the other side of the equation. So if we added x to both sides, and if we added 5 to both sides, in here we would get that 6x is equal to 30. Or I'm getting that x is equal to 30 divided by 6, which is 5. Okay, so that gives me the x value of intersection. I kind of want to know what the point of intersection is. So I could figure out where that value is if I go back into one of these original equation y equals and plug in 5 for x. It doesn't matter which one you choose. You should get back the same thing. And that could be a good check that you found that x value correctly. I'm going to plug it into the second one. So I would get y is equal to negative 1/5 times x, which x is 5 in this case, plus 7. So this is 5's cancel. I get negative 1 plus 7, which is 6. So one of our points of intersection is at this x equals 5 and y was equal to 6. Okay, so looking at that second piece and solving for x, let's distribute that negative sign. And so we would get x minus 1 is equal to positive 1/5 x minus 5. So I want to solve for x. I'm going to clear my fractions by multiplying 5 on both sides of my equation. Distributing the 5 on the left, we would get 5x minus 5 equals distributing 5 on the right-hand side. 5 times 1/5 x is just x minus 5 times 5, so 25. Getting variables to one side. So I'm moving all my variables to the left-hand side of my equal sign and moving all my constants to the right-hand side of my equal sign. So subtracting x on both sides and adding 5 on both sides, we end up getting 4x is equal to negative 20. And so in this case, dividing by 4 on both sides, I get x is equal to negative 5. So if we went back in again and plugged in this negative 5 into one of our original equations, we could figure out the point of intersection. So y is equal to negative 1/5. I'm plugging into the second equation. Y is equal to negative 1/5 times our x value we found, negative 5 plus 7. So y is equal to positive 1 plus 5, which gives me y is equal to 8. So the other point of intersection is negative 5, 8. Okay, so it asked us to graph this, and we have some pieces to help us graph. So the first equation, I can plot points or I can use some algebra in here. with transformations of graphs. I know that -1 inside that absolute value, that's a horizontal shift. And that horizontal shift is moving it to the right one. And that +2 is a vertical shift. And so technically, I would have 1, 2 as type of that, where that corner of my V shape is. And that's where x equals 1. That's where it changed directions. That's where we found in here when we rewrote our equations. Okay. So knowing that, if x is equal to, and we could plug in points if we want, but if x is equal to 0, plugging in 0 into this equation, I get absolute value of -1 is 1, 1 plus 2 is 3. I really kind of want to know, let's see what's at 5 and -5. So let's plug in -5. So if I plug in -5 into my equation for y equals absolute value of x minus 1, well, -5 minus 1, that's absolute value of -6, which is +6. And 6 plus 2 is 8. So I know when x is -5, my y value is 8. And then if I plug in +5 into the absolute value equation, absolute value 5 minus 1, so absolute value 4 is 4, 4 plus 2 is 6. So I have a point at 5, 6. Which I guess I didn't really need to do that because I have these points right here, right? So that's one of my graphs. And my other graph is y equals -1/5 x plus 7. Well, that's a line. It's in the slope intercept form. I know my y-intercept is 7, just looking at that. We actually found that our points of intersection was 5, 6, and -5, 8. So we have those other 2 points. We know that this is a line. So what we're trying to find in here is this area bounded between these 2 curves. So our integration, the problem is, in this problem, is that we have 2 separate equations for that absolute value equation. So let's look at this as breaking it down into 2 separate integrals. So I'm going to kind of divide it when x is +1. So looking at this, we're looking at the integral, right? My lower bound is -5. My upper bound, I'm changing equations because of that absolute value at 1. So I'm going to go to 1. My upper curve is the -1/5 x plus 7 minus the lower curve. But the lower curve for this piece right in here, we said was y was equal to -x plus 3 when we simplified it down. So minus off the lower curve, which is -x plus 3 dx. Okay, so now moving over to this other piece in here. So for that integral, we're starting at x equals 1. And we're ending at x equals 5. Our upper curve is still the same line as before, this -1/5 x plus 7. And then our bottom curve Our bottom curve is when x is bigger than or equal to 0, we're using this line y is equal to 1 plus x, or x plus 1. So minus that equation off. So minus the whole equation 1 plus x. And then we have this dx. Okay, so we've graphed it. We found out points of intersection. We found out what curves on top, what's on bottom, and then we've set it up so that we could go through and integrate this to find the area. So I'm gonna move this over so that we can have more room when we go through and integrate. I don't know if you want to clean things up. We might want to clean things up before we start integrating, because I notice we have like terms and that might just help us. It might just not be as messy. So let's do that. So if we distributed this negative in here, we have a negative 1/5 x. Maybe I can do some work on the side. A negative 1/5 x plus a x, common denominator. So think of this as 5/5 x minus a 1/5 x. That's going to give me a positive 4/5 x. And then I have this positive 7 for the first integral, and that distributing the negative, this would literally be minus 3. So 7 minus 3, this is plus a 4. And then we have this dx. Should have a plus in here. And let's simplify the other one. So if we distributed our negative 1, we technically have a negative 1/5 x, and our other x term is going to be a minus x. So again, common denominator. So we can write this as one term. I have a negative 5/5 x minus a 1/5 x is a negative 6/5 x. So then plus the integral from 1 to 5 of negative 6/5 x. And then for my constant, I have a 7 minus a 1. So this will be a plus 6 dx. Okay, so now I have a simplified integrand, which will just make our life easier once we take the antiderivative. So adding 1 to our exponent for that 4/5 x, we would get x squared. Divide by our new exponent, which is 2. Plus the antiderivative of 4 is 4x, and we're evaluating this from the bounds negative 5 to 1. Plus, so antiderivative of negative 6/5 x. So adding 1 to our exponent of x, we get an x squared, divide by the 2. Plus the antiderivative of 6 is 6x. And this is from 1 to 5. So we have common factors in the numerator and denominator. 2 goes into itself once, 2 goes into 4 twice. Over here, I have 2 and negative 6, so 2 goes into itself once, 2 goes into negative 6, and negative 3 times. Okay. So I have this 2/5. We're plugging it in our upper bound wherever we see an x, and our upper bound for that first integral is 1. So plugging in 1 wherever I see an x, I get 1 squared, all times that 2/5 out front, plus 4 times 1, minus, put parentheses around the whole antiderivative. And so now we're plugging in negative 5 wherever we see an x. So going through, we have, let's see, that 2/5 we have -5 quantity squared. And then plus 4 times -5. So going to the second integral, we're plugging in the upper bound. So we have plus, coefficient is -3/5. Plugging in our upper bound of +5. So I have 5 squared plus 6 times 5 minus plugging in our lower bound of 1. So we have -3/5 all times 1 squared plus 6 times 1. Okay. So going through and just order of operations and simplifying. So 1 squared is 1, so we have 2/5. 4 times 1 is 4, so plus 4 minus, I'm going to distribute the negative as we maybe clean this up. So -5 squared is 25. 25 divided by that 5 there is +5 times that 2 is 10. So we're going to get -10. 4 times -5 is -20 times the negative out front is +20. Okay, so looking over here, this -5 squared is 25 divided by the 5 in the denominator is +5 times the -3 out front. So that should give me a -15. Plus 6 times 5 is 30. I'm going to be distributing this negative. So 1 squared is 1 times -3/5 is -3/5 times the negative out front is positive +3/5. I'm distributing this negative. 6 times 1 is 6 times the negative out front is -6. So I notice that I have 2 fractions with a common denominator. So 2/5 plus 3/5 is 5/5, which is just 1, but I'll do that in a minute. We have 4 minus 10 is -6. -6 plus this 20 is 14. 14 minus 15 is -1. -1 plus 30 is 29. And 29 minus 6 is 23. So plus 23. Just make sure I did that right. And then 5 over 5, like I said, is 1. And 1 plus 23 is equal to 24. Let me just go check my math. I'll make sure it's correct. Okay, so the next problem in front of us is the integral 3 all divided by x times the natural log of x. And that x natural log of x is all in the denominator times dx. If you ever have an integral with a log or a natural log, you should clue u in. That's what you're going to choose your u to be. When you don't know how to integrate the natural log or log. And so I'm going to choose my u value to be the natural log of x. And so when we differentiate both sides of what we chose u to be, we get du equals, well, the derivative of natural log of x is 1 over x dx. And so we could multiply both sides of this equation by x, and we get x times du is equal to dx. So we're going to go in here, we're going to go back in and plug in what we have. So we have now the integral of 3 divided by x times, well, we chose u to be the natural log of x, so replace natural log of x with u. And then dx, we just found was x du. So things worked out nicely where the variable x cancels out. And so all we're left with in here is 3 all over u du. So this is the special case where we do not use that general power rule where we add 1 to our exponent and divide by our new exponent. So you have to think about what did we take the derivative of and got back 1 over u. Well, look at what we chose u to be. What we took the derivative of natural log of x, we got back 1 over x. So the derivative of natural log of u is 1 over u. So I know that antiderivative of 1 over u is the natural log of u. I'm going to put absolute values because we can't take the natural log of a negative number. And then we're going to do this plus c because it's an indefinite integral. Doesn't have bounds on our integration. Oops, and I'm not done because I need to go back and do substitution. We had chosen u to be natural log of x. So we have the natural log of the absolute value of the natural log. I'm going to put absolute value of x plus c. So since we've been dealing with substitution and definite integrals, we changed our bounds first, so we didn't have to worry about going back in at this point once we took the antiderivative and replacing u with it, the function in terms of x. And so with indefinite integrals, you just don't forget about that piece. Okay, so the problem in front of us is a definite integral. Our bounds of the integral is 1 to 4. And then our integrand is 1. And this is all divided by 2 square roots of x. That 2 square roots of x is times 1 plus square root of x. And that 1 plus square root of x is raised to the second power, dx. So it doesn't look very pretty. So let's try to see if we can clean this up by using substitution. And so to help us, it looks like we're going to have problems with what's inside the parentheses here, this 1 plus the square root of x. So let's try u equal 1 plus the square root of x, which is the same thing to help us take the derivative of is 1 plus x to the 1/2 power. So it's possible when you guys start these that you might choose something wrong with your u value and just have to restart the process. But let's see if we did this right. And so the derivative of u is 1 du is equal to, so the derivative of the other side, derivative of constant is 0, plus the derivative of x to the 1/2, bringing our power down front, 1/2, subtract 1 from our exponent, we get negative 1/2. So this is the same thing as 1 over 2 square roots of x, and I forgot the dx. So get dx by itself, and this looks like it's going to fall out really nicely. Get dx by itself, we would multiply both sides of our equation by 2 square roots of x. So we get dx is equal to 2 square roots of x du. Well, let's change our bounds now. Here we have x equals 1. So if x is equal to 1, we're going to go back in to figure out what u is. And so u in this case is equal to 1 plus the square root of 1. So 1 plus the square root of 1, u would equal 2. So we have the integral. Down here, u is equal to 2. And then that looks at x equals 4. So if we go back in and plug in 4, where we see the x in the equation for u, we get that u is equal to 1 plus the square root of 4. Well, square root of 4 is 2. So I get that u is equal to 1 plus 2, which is 3. So our upper bound is u equals 3. We have 1 all over 2 square roots of x. And then we had chosen u to be what was inside that parentheses. So we have u squared times dx, but we found that dx was this 2 square roots of x du. So this is really nice because what's in front of our du, 2 square roots of x, cancels with this 2 square roots of x down in this denominator. So we're integrating from u equals 2 to u equals 3. Well, 1 over u squared, it's not in that form that I know how to take the antiderivative of, but we could bring this up into the numerator and rewrite it as u to the negative 2 power du. Okay, so not too bad to take the antiderivative, add 1 to our exponent. So negative 2 plus 1 is negative 1. Divide by our new exponent, negative 1, and we're evaluating this from 2 to 3. So same thing as negative 1 over u, evaluated from 2 to 3. Plugging in our top bound first. So plugging in 3 wherever you see a u, we have negative 1/3 minus. Now plug in 2 wherever you see a u. So minus 1 over 2. So I have 1/3 plus 1/2. Common denominator. So I have 2/6 plus 3/6. Which gives me back 5/6. Oops, except I dropped off my negative. So it's actually negative 2/6 plus 3/6, which is 1/6. So the next example in front of us says determine the function f if f prime of x is equal to negative 3x plus 1, and this is all divided by the square root of x, and f of 1 is equal to 4. Okay, so we're given the derivative function, and if we take the antiderivative of the derivative function, that would give us our original function. And so we know that f of x is going to equal the antiderivative of f prime of x, which is equal to negative 3x plus 1 all over the square root of x. So I'm going to rewrite this a little bit. Square root of x, I'm going to rewrite as x to the 1/2 power dx. This is not in the form that I know how to take the antiderivative of, but because I only have one term in that denominator, I can split up my fraction as multiple fractions. So this is the same thing as taking my first term in my numerator, negative 3x, divided by x to the 1/2 power, plus second term in my numerator, 1, all over my denominator, x to the 1/2 dx. So by rewriting it like this, I can now use my rules of exponents, same base in the numerator denominator, which is x in our case. We are going to subtract the exponent on top. We're going to take 1 minus the exponent on the bottom, 1/2. So this would give us negative 3, 1 minus 1/2. So this would be x to the positive 1/2. Plus, and I'm just going to rewrite this 1 over x to the 1/2, bring that up to the numerator as x to the negative 1/2 dx. Okay, so we've manipulated it and rewrote it so that we now can take the antiderivative of this. And so the antiderivative, we're just going to add 1 to our exponent. So let's keep -3 there. Adding 1 to 1/2. So 1/2 plus 2/2 is 3/2. Times the reciprocal of our new denominator. So times 2/3. Plus, so adding 1 to -1/2. So -1/2 plus 2/2 is 1/2. Times the reciprocal of 1/2, so times 2. Plus C. So we need to figure out what C is. And they gave us enough information in here to figure out what C is. Maybe I'm going to rewrite this just a little bit with radicals and simplifying common factors in numerator and denominator. So right now I have f of x is equal to -2 square root of x quantity cubed. So the denominator is what index of our radical, and the numerator is what exponent you're raising it to after. It's easier to raise it after you take the root. So the next piece I have 2 square roots of x and then plus c. But we're given that when x is 1, our y value is 4. So I know that f of 1 is 4. So I have 4 is equal to, now let's go in and plug in 1 wherever we see an x. -2 square root of 1 cubed plus 2 times the square root of 1 plus c. So now we just have our variable c in here and we can solve for it. So we have 4 is equal to, well, square root of 1 is 1, 1 cubed is 1, times the -2 out front gives me -2. Plus 2 times square root of 1, square root of 1 is 1, so 2 times 1 is 2, plus c. Well, 2 minus 2, those cancel on the right-hand side, so we're left with what c is. C is equal to 4. So we know what c is. And so now we know what our function f of x is with those conditions. So f of x is equal to -2 square roots of x quantity cubed plus 2 square roots of x plus c, and c was plus 4. So in the following example, we have use implicit differentiation to find the slope of the tangent line to a given curve at a specified point. And so our equation is x squared times y minus y squared times x equals -2, and that point we're given is 1, 2. Okay, so notice that we have x and y on the same side of our equation, and it would be hard to solve for y in terms of x, if not impossible. And so we're going to use implicit differentiation. When we use implicit differentiation, y is a function in terms of x, so we have to think about it as using the chain rule. We have to multiply by that inside, and so we're just going to say that inside, because we don't know what it is dy dx. So I'm looking at this and I have an x squared times y and minus a y squared times x. So I noticed that when we take the derivative on the left-hand side, we're going to have to use the product rule on both of these pieces. Okay, so looking at the product rule, so recall we're looking at the derivative of the first function, x squared, so that would be 2x, times the second function, which is y, plus the first function, x squared, times the derivative of the second function. So derivative of y is 1, but we tack on that dy dx because it differentiated with respect to y. So that's just for that first term on the left-hand side. Minus, be careful because we have that minus and then we're using that product rule. So we need parentheses or brackets. That negative is going to have to distribute. And so if I take the derivative of my first piece, y squared, that is 2y, but it was with respect to y, so dy dx. Times the second, which is x, plus the first, y squared, times the derivative of the second, which is just 1, is equal to the derivative of -2. Derivative of a constant is 0. I'm going to rewrite this 2xy plus x squared dy dx. Let's distribute our negative sign inside the bracket. So we would get minus 2y dy dx minus y squared equals 0. We want to figure out what dy dx is. And so
should there be an x after the second dy dx?
yes, there should. And instead of putting it after, let's just put it in front of it, times x right here. Thank you. So we're gonna actually, oh no, that's not true. So let's keep the pieces with the dy dx on one side of the equation, and let's move the pieces without the dy dx to the other side of the equal sign. And we're going to end up factoring this dy dx out of the terms we left on the one side that have it. So let's just do that now. So if I pulled out dy dx from x squared dy dx, I'd be left with x squared. And if I pull dy dx out of -2yx dy dx, I'd be left with -2yx. Equals, so I'm going to add y squared to both sides. And I'm going to subtract 2xy on both sides. So this is equal to y squared minus 2xy. So now we can get dy dx by itself by dividing through by that parentheses, x squared minus 2yx. So we get dy dx is equal to y squared minus 2xy all over x squared minus 2yx. Okay, so that is giving us the slope of the tangent line anywhere, but now we have the value where we want it at this 0.12. So we're looking at when x is equal to 1, and we're looking at when y is equal to 2. And we're plugging those values in wherever we see x and y. So we get dy dx is equal to 2 squared minus 2 times 1 times 2 all over 1 squared minus 2 times 2 times 1. So if we simplify, we get dy dx is equal to 4 minus 2 times 2 is 4, all over 1 squared is 1, 1 minus 2 times 2 is 4. So we get dy dx is equal to 0 over -3 or 0? Okay, so the slope of the tangent line is 0 at 1, 2. Okay, so looking in front of us, we have a rectangular storage container with an open top. Is to have a volume of 30 cubic meters. The length of the base is twice the width. The material for the base costs $12 per square meter, and the material for the sides costs $8 per square meter. Find the cost of materials for the cheapest such container. Okay, so let's go through and kind of pull out some pieces. So we know what the volume is going to have to be. It's 30 cubic meters. So we're given that our volume is 30 cubic meters. But volume of a box is the base. Well, basically it's length times width times height. Let's write it that way. Length times width times height, we know is equal to 30 meters cubed. Okay, so now looking at this, it tells me that the length of its base is twice its width. So my length is equal to 2 times W. I'm not very good at 3D, but I'm going to attempt it. Okay. So this length in here, again, I know is 2W. And then we have our height. Okay, so if I go back in here and I plug in what we know for my volume, I have length, which is the same thing as 2W. So I'm going to go in here and I'm going to plug in 2W. So I have 2W times W times H is equal to 30. So I'm in here, I have 2W squared times H equals 30. So let's look at the cost of our materials. So the cost for the base, it's $12 per square meter. So if I look at my base here, let's look at how we find the area of that base. Well, it's length times width. So our base is equal to 2W, the area, 2W times W, or it's equal to 2W squared. And it tells me that that cost for the materials of my base is $12 per square foot. So this would be cost of base is equal to my 2W squared times the $12. So the cost of the material for our other sides. So the sides of our box. Okay, so if I look at this piece right in here, we have two pieces. Let's just look at this one. this front piece and the back piece, if I'm looking right straight on it. Well, this right here has the height and the length is 2W. So this area in here, and there's two sides with those dimensions. So we have, this is area, is 2W times H. And there's two of those, two sides. And then if I look at the other side of our box, there's two of them with these dimensions. We still have our height, but this case we have times that length here is W. So our area for those two pieces is equal to W times H, and there's two sides like that, so times 2. So the cost of the sides well, we know it's $8 per square meter. And so we're going to sum up the area of the two sides that are 2WH times 2. And I'm going to simplify that. That's the same thing as 4WH plus this area here, 2WH. This is all times the cost of the material, which is $8. Oops, I moved it in the wrong spot. Here's 2WH all times 8. Erase that. Okay, so I can simplify that even more because I have 4WH plus 2WH inside the bracket. And so this is equal to 6WH. The problem is we have W and H in here. And so if I looked at my cost of the area of the base, that just has a W in it. So let's go back to the one equation that we have up here with the volume, and we can rewrite our height in terms of W. And if we do that, then we have a function of all just W in there. So if I want to solve for H in here, I would divide both sides by 2W squared. So H in this case is equal to 30 divided by 2W squared. Or even better, H is equal to 15. Let's bring the W up into the numerator because that's going to help us when we go through and differentiate. So H is the same thing as 15 times W to the -2 power. So let's look at our total cost function. So our total cost was the cost of our base. Remember, our cost of our base we found was right here. And I'm just going to rewrite that as 2 times 12. So this is 24W squared plus the cost of our sides. And our cost of our sides here was 6WH.
Now you have to distribute the 8 for the cost of the sides.
Thank you. I don't know what I would do if you weren't here. I'd be crying at the end. Inside, not outside. Okay, so distribute that 8 inside. Actually, we could distribute it after we combine the like terms, right? And so that would be 6 times 8, which is 48 WH. But like we just said, H in here is this 15. So we can just rewrite it. So this is 48 W times H, which is 15 W to the negative 2 power. I don't really like that number. 15 times 48. That's 720. So this is going to be 720 W times W to the negative 2 power using rules of exponents. We would add our exponents. So this would be 720 W to the negative 1 power. Okay, so we were going in and we're adding now the cost of the sides, which was this. So plus 720 W to the negative 1. Okay, so we're trying to find cost of materials for the cheapest such container. And so we want to go through and we want to differentiate both sides and we want to find our critical numbers. And we're hoping that that critical number that we find is where the minimum occurs. And we want to show that. Okay, so taking the derivative of the total cost, I'm going to call that maybe C sub W. This is in terms of W. So taking the derivative of that, we get C prime of W is equal to general power rule. So 2 times 24, so that's going to be 48. Subtract 1 from our exponent, so it's just W. Derivative of 720 W to the negative 1, general power rule. So this is negative 720 W, subtract 1 from the exponent, it's negative 2. So we have 48W minus 720 over W squared. So we want to see when is this equal to 0 and when is it undefined. I see it's undefined at 0, which doesn't make sense because if I had my W as 0, I'm not going to have any volume. And then it's also when our derivative is equal to 0. And so setting our derivative equal to 0, 0 is equal to 48W minus 720 over W squared. We can clear our fraction, multiply both sides by W squared. If we do that, we get 0 is equal to 48W times W squared is 48W cubed minus 720. Yay. 48 actually goes into 720 evenly, so that makes life nice. So let's add 720 on both sides and then divide by the 48 to get the cubed by itself, W cubed. And we get that W cubed then is equal to 15. So let's take the cubed root of both sides. So we would get the cubed root of 15. Okay, I'm going to keep it in an exact form, and this is a meter. Let's just make sure that that's a minimum. So let's just test. We can either test by plugging in and seeing it's negative and then positive on either side. Or the second derivative test. I'm just wondering if the second derivative test might be easier. I don't know, either way. Let me just raise this. Okay, so the cubed root of 15 is about 2.5. I just kind of needed an idea of what to plug in. Well, let's plug in W equals 1. And we want to know if we plug this back into our derivative, is that going to be positive or negative? Well, I notice right away that plugging 1 back in for W, I have 48 minus 720. So that's less than 0. So I know my function is decreasing until I hit root 3, square root of cubed root of 3. No, sorry, cubed root of 15. Test something on the other side of this. So let's say W equals 3. So if we plug in 3 into 48, 48 times 3. That gives me 144. Keep a note here. Minus 720 over 3 squared, which is 9. 720 divided by 9, that gives us 80. So 144 minus 80, that's a positive number. So C prime of 3 is greater than 0. So this is increasing. So I can tell that W equals cubed root of 15 is a minimum. We need to go back and figure out what our other variables are. And so our height is equal to 15 all over the cubed root of 15 squared. Notice these have the same base. So using rules of exponents, this is the same thing. My height is going to be 15, 1 minus 2/3. So 3/3 minus 2/3 is 1/3. Or h is equal to also the cubed root of 15. And then our W, we have W, our width is, or length is twice W. So length is 2 times the cubed root of 15. Okay, so those are the values which gives us the dimensions that will give us the least cost of the material. And so we're going to have to go back into our cost function and plug that in. And actually, I guess I did a lot more work. Well, that's not true. I was going to say we could have just plugged it in here with W, but technically you would kind of want to know what the dimensions of your other sides are. But to get the total cost, of the materials, this would be 24 times W squared. So cubed root of 15 squared plus 720 divided by W, which is the cubed root of 15. So to me, that doesn't make too much sense of how much that costs without plugging into the calculator. So let me do that real quick. So plugging that into the calculator, we get that this is equal to, what's money, $437.92. So the total cost of that rectangular storage container with an open top would be $437.92. And we're in and that's minimizing the cost with a volume of 30 meters cubed.